Good morning, good afternoon, good evening, wherever you are watching. It's lovely to be here. Thank you so much for having me. I always enjoy. I think I was at the first one. I might have missed the last one, but I'm very pleased to be back. So in today's session, we're going to look at is how you can go about implementing machine learning inside Synapse. And I ran this session here before, so there will be some crossover, and we'll look at from the last one, and we'll look at some of the bits that have kind of changed and a little bit improved. All right, get my mouse to work, and off we go. So if you like this kind of content, I would always recommend you go and check out our YouTube. So if you're familiar with any of our stuff, you'll have seen Simon, always going on about Synapse. So we've got a whole load of Synapse videos up on our YouTube channel. So tiny bit about me. I'm Terry McCann. I run a company in the UK called Advancing Analytics. We are a consultancy which specializes in data engineering and machine learning. I'm a Microsoft MVP for AI, which basically means I spend far more of my time talking at events like this and probably not doing enough real work, as much as that's what probably the team will tell you. So really happy to be here. Right, so we've probably been through a lot around what is, Synapse and Synapse, how does it work? But what I want to kind of do here is dig in a little bit to, well, how does Synapse actually implement machine learning? So we'll have a little look at that. We'll move on to a bit of a definition around machine learning and some of the concepts we're going to look at just to set the scene. We'll then look at how that works inside Spark, and then we'll have a dig into some of the other features integrating Azure Machine Learning and cognitive services, okay? So you'll be familiar with this kind of picture, right, of a lot of the various bits and pieces that we have. And this has changed again since, right? It changes kind of every single month. But when we're looking at machine learning, we've got a couple of different options. So we've got in terms of scoring and training. So scoring being I've got a model and I just want to get a prediction, and training being I want to use some compute to actually create a model that I can then use to score with. OK, so in terms of our SQL engine and dedicated SQL pools, we have the ability to just score a model. And that uses a particular model format called ONNX, ONNX, which is the Open Neural Network Exchange Protocol. And so that's an interesting one that we won't go over today, but I am running a full day pre-con pretty much on just this topic of machine learning inside Synapse at SQL Bits, as Victoria mentioned. So do come and have a look at that, where we'll dig into a lot of these additional bits and pieces of ONNX, etc. Then with Apache Spark, we have the ability to do scoring and training. Then we have integrations in terms of Azure Machine Learning, as well as cognitive services for a couple of different techniques. So we'll have a look at all of that today. So Synapse looks like this, right? It's a combination of multiple different bits and pieces. And we're really going to be focusing on that bit in the middle, which is the Spark pool, which is how we can do machine learning in Spark, okay? So Spark pools are always interesting. They slowly improve over time, still not quite where I'd expect them to be, still not quite where we'd hope them to be in terms of other platforms that are available for running Spark. But things that you should be aware of, right, that we can write in different languages. We've got the ability to write in Scala, in Python, C#, SQL, as well as other languages such as Cypher. If we're looking at graph query languages, there's a whole variety of options that we have. And we can do a whole load of different things, including machine learning in here, okay? But Spark can be very complex, and it can be, and certainly machine learning is an interesting approach with Spark. It's a lot lower level than you might be used to in other languages. Session management is interesting, and we'll probably come across a couple of problems as we try and run things today, but we'll see how we get on. Right, so high level, what is Spark? So you can think of Spark as a core set of services that were once built around Hadoop, and as Hadoop was very disk-based, Spark looked to take all of that processing and make it in memory. It's an entirely open source tool, which was largely created essentially by the team from Databricks, so Matei Zaharia, and then eventually donated to the Apache Foundation and now has since been embedded into many data applications. The core around Spark then extends into a couple of different ways of working. You've got data frames, machine learning, graph frames, and as well as streaming as well. So you can do all of these kind of things just by extending from the same code base, which was always a nightmare in Hadoop. The way that it works, this is the Spark architecture. That's a Simon Whiteley term for you, for any Simon fans out there. The Spark architecture looks a bit like this, okay? Whenever we're talking about Spark, we're talking about an MPP-based system. It's a massively parallel processing engine. And what that means is that we're working with a distribution. And what that means is that we've just got more than one machine, right? So here you'll see we've got a driver, and then we've got two individual workers, okay? So I've got a cluster of 3 machines. When I'm doing actual work, I'm typically only using those 2 machines, which are my workers, and my driver is there to help and orchestrate everything so that it goes right, okay? On that driver, you'll see this thing called a Spark context, and it's this context that interacts with our workers and helps us distribute data, okay? And so this is a very small cluster. You could scale this cluster up, right, to be 4 workers. It could be 50, it could be 6,000. It really depends on what your requirements are and also what your limits are. As you kind of scale, you introduce different problems that you might not be familiar with if you've only worked in a kind of SMP way, a symmetrical multiprocessor, such as SQL Server, right, on a single box. Wherever you have distributions, things just get more complicated because you've got data in multiple places and just it all gets a bit awkward. So if you don't need to scale out, I'd always say just don't bother. Just do it somewhere else. But if you do need to scale out, then Spark's a great way to do it. Always worth noting that everything we're looking at here is underpinned by the JVM, so a Java Virtual Machine. So things that you're, again, might be familiar with from a kind of Windowsy way of working, you always have to bear in mind that there's potentially serialization happening between Java languages and non-Java languages, okay? So distributed compute works a bit like this, all right? I submit a query, and that might be in Python here, so PySpark. That goes off to my driver, and my driver distributes that query to each one of my workers, okay? And now my workers will go off to my data store, which might be something here like Azure Data Lake Gen 2. Azure Data Lake Gen 2 is a Hadoop-based file system. So it uses the kind of standard protocols in HDFS, which enable things like your files to be sharded into multiple pieces automatically for you. And what that means is when you land one big file, under the hood, it gets chunked up into much smaller files. So when we're working with a distribution of machines, each one of our machines can just go and read a small part, and it just happens really quickly. So we get huge performance improvements when we're kind of hooking all these pieces together. Each one of our workers will kind of grab that data back, pull it back up, and then we will do our calculation on each one of those machines, right? That's kind of the core of MapReduce. That's what MapReduce is trying to do, right? We take a function, we map it to where our data is, we calculate that function, we reduce the results, we shuffle them around, and then we return them back to our application calling us, right? Same thing which is kind of happening here. So Spark adds that bit of complication, but sometimes you need it, and most people nowadays do need that kind of scale. So machine learning on Synapse, right? It's worth to call out a little bit of the machine learning process just so that everyone knows what we're kind of stepping through. Now, this process comes from I think it was actually like a GDC conference once, so the Google Developer Conference, and it was called the 7 Steps of Machine Learning. You've got it there. It might have been from, it says TensorFlow there, so it might have been from the TensorFlow conference. But these 7 steps look like this, right? We go away, we gather some data, we prepare that data and we visualize it, we select some kind of algorithm, we train a model by taking our data and our algorithm, and we just kind of put the two together, right? We evaluate that model to see how well we've done. We might then go and do some hyperparameter tuning, which is tweaks to that model to essentially make it work a lot better, or in theory work better. And then we will test our prediction. If we're happy, we'll put that, we'll potentially just put that live, right? We'll deploy it. So we will kind of go through a variety of these steps to kind of see how this actually works. I've added number 8 there because everyone always forgets about number 8, right? It's okay to get to this step, but once you got to this step, if it's not live, then we never offer any value for what we're actually doing. And then it's just a fun waste of time. It's definitely a nice fun waste of time though. So the formal definition, right? Machine learning provides a system the ability to automatically learn and improve from experience without being explicitly programmed, right? That's the key here. We're not explicitly programming how something should happen. What we're doing is we're using large amounts of linear algebra to essentially create large matrices and do matrix multiplication so that we can then work out a nice kind of path through our model, which gives us a generalized approach to the problem we're trying to solve. But we're not explicitly saying do this, then this, and this, and this, right? We're letting our processes inherit and infer what we're trying to produce. It relies on an underlying hypothesis of creating a model, and it tries to improve it by fitting it with more data over time. Now, a reason I kind of call out some of these words, such as improve and fit, is because these are words that if you're not used to machine learning, you might not be familiar with. And in the machine learning world, we use these terms so that we can alienate people from our industry, so no one comes to play with us. Or rather, not quite right. But you'll see that there's a lot of commonality between some of the data words that we're very familiar with and machine learning. Fit just basically means we're going to train our model. Cool. So types of machine learning, right? You can generally break this down into shallow-based machine learning and deep learning. Today, we're only going to focus on shallow machine learning, so I'll kind of just skip over deep learning a little bit here. As mentioned in that 7 steps, right, we take some input data, we do something to it, we kind of go through, we do feature extraction, feature engineering, and we get our data to the point that it's going to generalize to the problem that we're trying to solve. Then we might try and do something with it, right? Do some kind of classification, okay? And then we get our output. So they say, right, that this kind of section here, data input and feature extraction, is accountable for 80% of machine learning. And then they say the other 20% is just spent complaining about, you know, the data and the feature engineering. I honestly think that it does take a lot of time, but that's the fun part. So that's where you can really apply your skills as a data scientist to actually make something work well. On the deep learning side, assuming that you're doing something which fits into like a convolutional neural network, such as images or audio, anything that's tabular, there's no silver bullet, unfortunately, you still need to do the work. But for something like image-based data where we can do things like convolutions, then we can do stuff like automatic feature extraction and classification by applying a deep neural network, right? I've got tons of videos out there in the wild about deep learning in Spark and other bits and pieces. So by all means, go track one of those down. So shallow machine learning. I'm joined by my mustachy friend. And my mustachy friend here, he says, hey, I'm trying to predict how much somebody will spend the next time they come into my store. Okay, this could be a common kind of scenario. Someone might come to you and say, that's what I'm trying to do. And if we try and boil this down, really what we're saying is that I want to predict how much somebody will spend. And spend is an interesting one. So spend is what we class as a label, okay? And that label is what we're trying to predict. We might have examples such as clustering, where we're looking at our data and we're not necessarily trying to understand a particular thing, but we're more just trying to look at our data and find trends and commonality in that. There we don't have a label. But in this example, we do have a label, and that label is spend, right? So we take some data and we're going to plot it, and we're going to plot one feature against another feature here, okay? And a feature is just another one of those terms to say, this is an attribute in my data. This is a column of my data. It might be a column that was in my data to start with, and it might be something that I've generated, okay? And we're going to plot it. And as if by magic, a trend is emerging. Oh, we found a wild trend. Look at this one. It's very, very linear, right? You may assume that I've contrived this stuff to make an example, and you'd be right. So what you can see, right, is as we plot one feature against another feature, we can see that we've got this nice linear relationship, and this gives an example of regression. Now, the reason I call this one out is when we go and look at Spark, we'll look at regression as an example, just hopefully set the scene a little bit. Okay. So we touched on briefly about clustering. We saw an example of regression. Another example might be classification, right? So whether or not something is fraud or not fraud, true, false, yes, no, right? A binary outcome, or it could be a multi-class or a multi-label problem as well. Just out of interest, show of hands, or just put in the chat somewhere, right? Who commits fraud? Just going to wait. Just everyone could just put that notes in. And also just put your phone number and home address, please. Just be really helpful for me, just if you do commit fraud. Okay, moving on, right? Fraud's quite hard to detect, but we've got some, have a look as well. We've got other stuff on that. And typically this kind of gets broken down, right, into unsupervised learning and supervised learning. And the only real distinction that we have here is that our unsupervised doesn't have a label and our supervised does have a label. Again, that example being spend, right? So in a supervised approach, and what we're going to do today, we're going to do something like this, right? We're going to take a load of data, we're going to split it, generally 70-30, 60-40, whatever works for your data. And we're going to create two sets. We're going to create a training set and an evaluation set. So we're going to use that training set and we're going to pass that through our generic algorithm. We're going to do a whole load of tweaking to that, essentially a lot of linear algebra, and then out pops our lovely model, right? And then we're going to take that data that our model has never seen before, and we're going to say, how does this compare? So create a prediction based on this data, and then let's look at what actually happened, and let's evaluate it. And if our model says true, and our actual data said true, we're like, cool, tick. It says true, true, tick. False, true, okay, wrong, right? So of those, I've got one wrong out of 3 currently, and I can start working out how accurate my model is. And then if we're happy with it, right, we'll take that model, we'll put it live, we'll show it new data, and we'll get new predictions. Fantastic, okay? That's what we're trying to do. So how does this all work inside Spark? Now, Spark's had a long history, right? If you're completely new to Spark, Spark's been around, I think we're in the 11th year of Spark at this point, okay? And in that time, it has changed a lot. And there are, whenever we teach people Spark, we'll always say, like, if you try and Google a problem, you will typically find a load of different answers, right? Stack Overflow is great for that, but there are lots of history and there's lots of rubbish now, you know, out-of-date rubbish that's in Stack Overflow. And so one of the things you'll find is you might search for something and you'll find an answer built in what's known as an RDD, a resilient distributed data set. Now, RDDs are the kind of old way of working with Spark, and the new way is data frames. RDDs, you had to really program yourself, and data frames work in a declarative way. There's an engine behind it that interprets what you want to do and submits that back into RDDs in the best way possible. So we always recommend work with data frames and don't work with RDDs because they're just painful. The same thing applies with machine learning. There's MLlib, which is the kind of RDD way of working, and there's SparkML, which is the data frame way of working. So again, focus on SparkML. Annoyingly, still the terms just get intermixed loads. So you could read something about MLlib that's actually using data frames, and you could see something about SparkML, which is actually talking about an RDD way. So just be careful when you're working with this stuff. It can get a bit annoying. Saw our types of machine learning, right? But how does this work inside Spark? So let's say we've got this kind of flow, right? You are starting over with your source systems, you're doing some cleansing, some data processing, that feature engineering, and then, nice, clean structured data comes out of it that you're really happy with. You're then going to do some modeling, right? And you're going to typically kind of iterate over different approaches. You might try a decision tree here, so assuming we're doing some kind of classifier, and then you'll get some kind of response at the back of it, and you go, it's not quite what I want. I'm going to try a logistic regression. And actually, now I'm going to try a Bayes approach now. I'm going to try some other approaches and some other bits and try a few different things. And then I'm going to actually say, right, I'm happy with that one. I'm going to tune it, and then I'm going to evaluate it, although you do evaluation throughout. And then I'm going to pop that model into production. I'm going to run that. Okay. So how Spark implements this is with a number of key components. They are transformers, estimators, pipelines, and evaluators, okay? And as I mentioned at the start, Spark is a lot lower level in its implementation of how it works compared to other frameworks such as scikit-learn or XGBoost. There's kind of a lot more stuff that you need to do to get Spark in the right format for actually predicting, okay? But we'll look at that. So to kind of run through these, a transformer essentially takes a data frame and it will transform it by applying something to it that it can just kind of infer by just essentially just looking, not even looking at the data, but taking a column and applying some change to it. And it will produce a new data frame. So data frames are immutable. So the assumption here is that whatever you're doing with these transformations, that you will take one data frame and create a new one. You can just overwrite the existing one, but generally just kind of create one and create a new one. Now, Spark is a lazy language. So each time you're doing this stuff, you're not actually executing anything. You're just building up a DAG. So you're building up a directed acyclical graph. And that graph is then what gets interpreted and actually made into your actual RDD components, okay? So each time you do this stuff, and you've got like 2 terabytes of data you're training with, you don't need to worry about it. It's only when you actually want to fit your model that it will go away and actually do the grunt work, okay? So you could be converting a data type, could be changing a categorical value into a numerical value, could be something like this, right? You'll know it's a transformer because we will call transform on a transformer. It's mind-blowing, right? Primary use of this is feature engineering and pre-processing, okay? Example, right, might look a bit like this, okay? So what we've got here is, have I got my Zoom installed? No, of course not, schoolboy error. 2 seconds, and away we go, right? So it might be something like this, where I've got from PySparkML, I want to import this thing here, the regex tokenizer, which is a great name, the regex tokenizer. All it does is it just takes a sentence and breaks it down into individual words, but it sounds cool. It's not quite as good as the binarizer, which just makes something binary or not. But again, binarizer sounds awesome. So right, we import our regex tokenizer here. We instantiate it by saying, I'm going to create this thing here, which is a tokenizer. It has this input column. So it's going to find something in your data. And it's going to produce this output column. And it's going to use this regex pattern. If any of you have mastered regex, I bow down before you. I will never master it. I will always Google it. It gets me by. Do not worry. And then what we do then is we say, I'm going to create this new data frame. You see, I called it like DF. Always got a data frame somewhere in there. And I'm going to say, I would like you to transform this original data frame. So here I'm kind of going data frame to data frame, and I'm moving one to the other. And then I'm just going to view it. And so what I should have here is my original data frame plus this nice new tokenized column added to it. And all of the stuff we'll look at follows this flow of import something, instantiate it, take one data frame, and create a new one with the output of applying that transformation, okay? We've got estimators. Now, a lot of this stuff, whenever I go through this, don't worry, it'll make a lot more sense when we see a demo, okay? Estimators we will fit, okay? Estimators need to be fit. Now, an estimator, you can think of an estimator being anything that needs to see your data in order to be able to make some kind of transformation. So if you think about imputing missing values in your data, right? You've got a column of your customers' ages, and there's 100,000 in there, and you've got like, I don't know, 200 that are missing. What you could do is you could just say, well, I want to find the average age for a customer, and I want to fill that in for every blank customer that I have. You could do that. It's probably not a very good strategy, but you could do it, right? In order to do that, you need to read that data in first, work out the average to then be able to apply it, right? There's 2 steps there. Read it in and work it out and then apply it. This is the same thing. Estimate it and then transform it, okay? So all estimators will become transformers and eventually will be used to transform your data, but they've got a pre-step, right? Examples might be missing values, or it might be some of the lower level things that we need to do, such as vector assembly, vector indexing, and then also our algorithms, okay? So again, if you think about an algorithm, it's a two-step process. You need to fit it with your data to then transform your data, okay, to actually do your prediction at that point. Bear with me, we'll get there. Pipelines are great. Essentially what you do is all of these transformations, you'll queue up in a pipeline. So you'll have dirty data go in one end and you'll have nice predictions come out the other end. And when it comes to productionizing that workload, you productionize the pipeline and not the individual components. So that massively simplifies what you're trying to do. Okay, it's really useful. So pipelining is really good. Evaluators, did we get a good prediction or not, right? That's pretty much where we're going to look. Okay, let's go and actually have a look at some stuff. Right. So I have got a Synapse workspace set up here, right? But I've got a couple of things in here. So I've got my Synapse workspace, but what I've also got in here are a few additional things. So I've got a Synapse ML workspace. So we talk about how we can connect the two up. We'll look at that, and I'll be using essentially another workspace for that. I've got Key Vault, so I need Key Vault as well. I've got some other bits in here which aren't showing. Let's just refresh this. There they are. The little cheekies were hiding. I've got this one here. So I've got an anomaly detection in here, and I've also got another cognitive service in here as well. Okay. So I've got my workspace, I've got my cognitive services, and I've got Azure ML so that we can look at all of the key components. Got a dedicated SQL pool in here as well for doing things like predict and T-SQL. But if we hop over to get started with ML in Synapse, you've got a couple of different ways. You can just kind of get going, or you could come in here and you could have a look and just say, I want to create something new. Or you could look at one of the kind of great examples, and there's lots of different examples available that you can get started with. Now, how we're going to get started is I've already got built a Spark pool, the Spark pool here called machine learning, which is a medium size. So it's 8 cores with 3 nodes. I realize that I've had this basically running for about a year now, and I have no idea how much it's cost me, but well, it's always fun to see those things, but we'll have a look. So what I've got is I've got a couple of notebooks already open over here, and I've got some data. Okay. So the data that I've got here is called bike rentals, and this bike rental data has a whole load of different columns in here. What we can see here are things like we've got the date that's happened, and all the way down here we've got the count. And so what this data is it's how many bike rentals have happened per hour. I think it comes from San Francisco. And so what we can do is we can look at things like the temperature, the average temperature, how humid it was, what the wind speed was, whether it was a working day or a weekend. And ultimately what we're trying to predict is this thing, right? Is the count. How many bikes will be rented if it's a sunny day in February? Okay, that's what we're trying to get to. So I've just imported that data and I've registered it in a database here called Synapse ML, and I've got that running. Now you'll see this is a lake database, right? This is using Hive, and I've just made an external wrapper over the top. So looking in here, let's zoom in a teeny bit because it's not the easiest to see. What I've got is a notebook, and you'll see it's timed out, but I ran it before, so we'll just walk through it. And what we're going to do is going to import a couple of different packages here. So I'm going to import pandas and seaborn if we need to do any pure Python-y things. And I'm going to import this function library here. So pyspark.sql.functions, and I'm going to import it as F. And the reason that we do that is because PySpark SQL functions has a load of the Python base functions overwritten in it. So if you want to do things like sum or counts or things like this that you might do for in Python, anything like or what do you call it? If you're just trying to do like list interpretation, you're trying to sum up the values in a list, or some of these things, you won't be able to do. It'll throw up these really annoying errors that just don't make a lot of sense, and it's because you've overwritten them. So always try to keep with importing stuff as a value, right? Anywho, we're going to import our data here, and so I'm just going to use this bit of syntax here, which basically just says Spark. And if you remember, we had that picture, right, which was like the driver and the two workers. And I said on the driver, you've got this thing up here, which is the Spark context. Basically, yep, that is the Spark context, this thing here, Spark. And I'm saying, hey, Spark, can you go and read? And if you remember, we've got our data set down here, which is potentially nicely chunked up into multiple pieces. Can you go and read that data? So each worker will read the data in. And now I'm saying that the data has got a header, and I'd like you to infer the schema, please. So I'd like you to look at it, have a look at the columns, work out the data types, and then instantiate this thing here, which is my lovely data frame. All right, and it's a CSV. And we can display that data, and it looks a bit like this, right? We can go, lovely. Lots of interesting data. We can see the counts here. We can see kind of what they range in their values. We could try and do a chart and look at potentially instance, a terrible thing to look at. But we could have a play around with this, right, and try and do some interesting things so that we could start getting a better idea. We don't want the instant, we want the count, right? And start having a look at by day, or more interesting, something like by hour. If we can find the hour column. Not by day and by hour, that's far more complicated. Cool, right? And so you start seeing an interesting thing here. You start seeing that when it's about midnight, we have some bike rentals, and then over the wee hours of the morning, we don't really have any. As we start getting into core business hours, boom, that's where we see lots of sales. Kind of calms down a little bit while people are getting to work, and then boom, again, we get a very similar thing around dinner time, and then it kind of just tails off again. So we can use this to just get an idea of what's kind of happening, and it's pretty good. I would love to be able to switch these around. Carrying on, we could cache this data, right? So Spark is in memory, and by default, it's not going to cache your data and persist that data in memory. It's just going to kind of hold it in memory. We could say, actually, can you please cache my data? And it will hold that in memory for you. You've got a limited amount of storage on each of these machines. I think I said I've got about 16 gigs per machine, and Spark typically takes about 8 gigs of that. So you've only got about 8 gigs of memory that you can work with. So each time you cache, you're just kind of taking up an amount of that. And if you take up too much, you just get memory issues. Okay. Here we've got a little bit about what we're doing. And now we could call something like this. So I want to call df.describe. And what describe is going to do is produce me some summary statistics of the data that we're looking at. So we can see here that we've got just shy of about 18,000 observations. Observations just being a fancy word for number of rows, right? And we can see if we scroll along to something like the count, right? So on this count here, we've got 17,000. And what were these things here? So the mean, the standard deviation, and the minimum and the max. So the minimum rental in one area was 1, and the maximum was 977. We can see that the average is 190, and there's a standard deviation of 181. So looking at these two numbers, even in the most crudest approach of saying, well, what's 189 plus 2 181s? That's a lot, less than 977. So we've probably got some outliers in this data that we'll need to explore, because potentially it's not going to generalize that well for us. We could start having a look at our data, and we could say, how well correlated are each of these attributes against what I'm trying to predict? So I'm trying to predict here the count, and I can have a look at these, and I can see the instant is quite well correlated. Instant is just an ID. It's just a bit weird that it's quite well correlated. It's mainly because of the way that it's written into the database, but you can ignore it. Season, year, month, hour. Okay, you know, we can see these aren't crazy. One basically here being the, you know, it's a straight line. Then we've got these two down here, casual and registered. And what we can see here is registered is 97% correlated. It's a 0.97, which basically means if you compare registered and the count, it's basically a straight line, which would show that we've got a term called label leak. So these two values here are highly kind of indicating to me that I don't want to use these because they potentially are leaking our label. And if you actually read what they are, if you add them together, they equal the count. It's basically, are you renting a bike as somebody just going up there and saying, hey, can I rent this bike? Or have you like gone on an app where you're a registered user and said, yeah, I'm going to rent this bike from this place? So it's, if you basically, you wouldn't have that data in reality. So we want to exclude it. So we're going to drop a couple of columns here and have a look again. So now we've dropped the instant, we've dropped the date, we've dropped the casual. The reason I've dropped date is because it doesn't really add anything for us here. We're mainly interested in which particular day on which particular month instead of the actual date. Okay. The world's simplest feature engineering, is it in the morning or is it in the evening? Now, what would be a better feature here would be, is it in core business hours or not? Okay, so we could do some other interesting things if we wanted to. One other thing to also call out here is this data has already been cleaned up for us. So you'll see when we look at year is year 0 or year 1. It's not like 2012 and 2013. It's been encoded for us. Same with month, hour, and things like temperature here, right? 0.24 doesn't mean it's 24 degrees Celsius or even 24 degrees Fahrenheit. It means that it has had a Z order index applied to it. So it's been mean centered. And all that basically means is that we've tried to standardize the range. So at its highest, at like 1 or any number close to 1 shows extremities, and anything close to 0 shows extremities in the other way. Okay, and that's all been applied for us. And I think it might even say up here that water has been applied to it somewhere here. There you go. It says this is a normal range in Celsius. However, it's derived by looking at the minimum and the maximum and then trying to scale it. Okay. And then what we're going to do is we are going to come through and we're going to test and train our data. So we're going to create 70% going one way and 30 going the other. And then with that data, we are going to start looking at some of our transformers. Okay. So we've got a couple here. We've got an assembler, an indexer, and a min-max scaler. Now we don't need that because our data's already been scaled. But if we wanted to, we could use that to scale. And so what I'm going to do is I'm going to say, I'm going to set up an assembler. I'm going to set up an indexer. And what this is that when you train a model with Spark, Spark only wants you to pass in a single column. And that single column should be in a dense vector type. And so what this is going to do, you'll see the vector, right, is create a dense vector for us that Spark can then use to train the model. This is kind of where, I mean, if you take something like scikit-learn, you just give it a pandas data frame or a numpy array. You don't have to give it a dense vector. It kind of abstracts that away from you a bit. Then we've got our actual model. So here I've got a decision tree regressor, and I'm just saying I'm going to create that. Then I could have a look here and print out the parameters. And if we have a look at these parameters, one of them you'll see here is the label column. So what is it that you're actually trying to predict? And then there's other things in here that we can look at, such as the maximum bins and the maximum depth. And so this is a decision tree regressor. So basically what you end up with, right, is something that ends up looking like this, right, and another side going, and then lots of other bits coming off here, right, And so each time something falls down here, it end up with like 0.1, 10 bike rentals, 100 bike rentals or something. So you'll get lots of repeating values because it's just going through a decision tree. And we'll see that in a moment. So we're going to set that label. Then I'm going to set up a pipeline. And all this pipeline is doing here is it's saying, do my assembler, do my indexing, then do my decision tree. Now you might have like step, like tons of these in an actual model as you curate your data. But for us, we just got something simple. Okay, and that creates this idea of our pipeline. Then to actually train our model, now what we need to do is we need to take our pipeline, which is now essentially an estimator, and we need to fit it. Once it's been fit, that's the process of training. This thing here, our model, becomes a transformer. It all makes sense. It all makes perfect sense. I know what you're saying. We've got the option if we want to write it out. So I can say model.write, and then I save that model somewhere, and I can read that model back in. So now to actually create some predictions, what I need to do here is say model.transform. That will transform my data here, and it will add my predictions. Okay. I can evaluate this here by using a couple of evaluation metrics. So the root mean squared error and the R² value here. Root mean squared error essentially being a generalized amount of what's wrong in each prediction, and the R² being the coefficient of determination, essentially how well correlated our data is. The closer to 1, in theory, the better the prediction. So looking here, 6.5, yeah, it's okay. It's not perfect. And we're wrong on average by 108 rentals. It's pretty bad, right? We want that to be a lot lower. We want that to be in kind of like the 10s maximum. So there's a lot of work that could go into this to improve it. We use this as an example, typically in training classes, and then we ask people to correct it and change it and actually improve on it. Now you can get the number down to about 10, 11, 12, 13 wrong and get a much, much better model if you try different processes, okay? And then the last bits we have here are our predictions. And what we can see here is in our predictions, the actual value over here was 22, and we predicted 62, 25, 62, 33, 62, right? That's because it's going through that decision tree. But we've got some nice predictions. Now, that's kind of how it works in Spark. I've got about 2 minutes, so what I'll do is I'll quickly try and show you other options you have. Other options you have on our data here, I can choose machine learning, and I can choose to train a new model using AutoML inside Azure Machine Learning. That gives us classification, regression, and time series forecasting. And I can come in and I can say, yeah, I want to do regression. I want to use my Synapse machine learning workspace that I created before. I want to create this new experiment, this new model. The target column I'm trying to predict, right, is the count, and I'm going to use my Spark pool to do that. That will go away and generate a ton of models and run each of them and give you some interesting models back that you could then productionize. Last one here is I've also got this bit down here, predict with a model, and I've got the option to reach out to a cognitive service for anomaly detector or sentiment analysis. So I could say, I want to have a look at anomalies, and it's going to claim I don't have a cognitive service attached, although I definitely do. No, it doesn't want to. Okay, but we don't have time anyway. But what you do is you select your granularity, you select your timestamp, you select what you're trying to predict and any groupings on your time series, and then hit go, and it will produce you a notebook which you can then run, which will use the cognitive service. So really useful and a good way to get you started. So we'll finish off on the last slide. So when should you use Spark, right? What I would always say with Spark is Spark's great for many analytics tasks. Whether your data is if your data's in the cloud, we'd always say pretty much now Spark is your go-to for a lot of your data processing or things like serverless. But Synapse still might not be the right place to run SparkML right now, but hopefully it will improve in the future. And generally, we're seeing month on month that things are improving and there are better integrations. If you do want to get in contact with me, please do. You've got my details there. You can find me on Twitter at SQL Shark. And thank you very much for your attention. Enjoy the rest of your day. And yeah, hopefully I'll see you at something like SQL Bits in the future. Thanks very much.